In the vastness of our solar system, where planets, moons, asteroids, and comets dance in intricate orbits around the sun, there exists a collection of objects so unusual that they defy the categories scientists have used for decades. These celestial oddities, neither fully asteroids nor fully comets, have puzzled astronomers and forced them to rethink the boundaries between these two familiar classes. They have come to be known as dark comets, a name that captures both their mysterious nature and the fact that so much about them remains invisible and unexplained. Despite their subtle appearance, these recently discovered space rocks might hold answers to some of the most fundamental questions about our cosmic origins, including the long-debated mystery of how water first arrived on Earth. At the same time, their unpredictable behavior suggests they may pose a greater threat to our planet than previously understood. What makes their existence even more fascinating is that humanity now has a chance, perhaps by complete coincidence, to observe one up close. A Japanese spacecraft is already on a trajectory that will bring it face to face with one of these objects in the early 2030s, and when it finally reaches its destination, it may give us the first detailed look at what these enigmatic bodies truly are. The story of dark comets begins not with dramatic discovery, but with a subtle anomaly. In 2016, astronomers observed what they initially believed was just another asteroid, one of millions that orbit the Sun, most of them located in the asteroid belt between Mars and Jupiter. Asteroids are generally inactive, rocky, airless remnants from the early formation of the solar system. They move predictably under the influence of gravity alone. Comets, by contrast, are icy travelers from the outer solar system. As they approach the Sun, their frozen surfaces heat up and release gas and dust, forming the iconic glowing tails that can stretch for millions of kilometers. These jets of gas produce small but measurable accelerations, tiny pushes that alter cometary orbits in ways that astronomers can track. But the object spotted in 2016 refused to follow expectations. Although it lacked a comet's glowing tail or any visible sign of activity, it moved as though an invisible force were pushing it. Its trajectory showed small deviations, fractions of a meter per second, from what gravitational calculations alone predicted. These deviations were unmistakably similar to the non-gravitational accelerations seen in comets, yet all the visual evidence suggested it was just a dull, inactive piece of rock. This contradiction sparked intense curiosity. If something behaves like a comet but looks like an asteroid, what exactly is it? The intrigue deepened in 2017 with the sudden appearance of a highly unusual object passing through our solar system. It was elongated like a cigar, stretching somewhere between 115 and 400 meters in length, and it was given the name Oumuamua, a Hawaiian word meaning scout or messenger from afar. It soon became clear that Oumuamua was not from our solar system at all. It was the first known interstellar object ever observed passing through, arriving from deep space before circling the Sun and continuing its journey outward. Yet it too exhibited strange accelerations without a visible tail. Some scientists proposed it was shedding hydrogen gas in a way too faint for telescopes to detect. Others suggested exotic explanations, such as a fragment of a shattered exoplanet, or even an ultra-thin natural sail-like structure propelled by sunlight. Whatever the cause, Oumuamua challenged almost everything astronomers thought they understood about how small celestial bodies move. The plot thickened further in 2023, when a research group led by Darryl Seligman at Michigan State University identified 6 additional objects orbiting the Sun that showed similar mysterious bursts of speed. Unlike Oumuamua, these 6 objects are native to our solar system. They follow asteroid-like orbits, have no visible dust or gas emissions, and appear completely inert. Yet they undergo sudden accelerations up to 1 nanometer per second that gradually shift their orbits by hundreds of kilometers over the course of a few years. Though tiny, these forces were enough to be measured and confirmed. Their size, between 4 and 32 meters across, makes them especially hard to study, as they are too small and too dark to reveal much through telescopic imaging. and yet their behavior signals that something beneath their surfaces, perhaps sublimating ice or pockets of volatile material, may be pushing them like miniature thrusters. Around the same time, Seligman's team made another discovery involving a known near-Earth asteroid called 2003RM. This relatively small asteroid, roughly 300 meters in diameter, had been observed for years and was thought to be a typical near-Earth object. But upon closer examination, its orbital path also showed unexplained non-gravitational forces at work. This suggested that 2003RM might also be a dark comet, one that occupies an orbit perilously close to Earth's own. This revelation raised a sobering point. If some near-Earth asteroids are actually dormant or hidden comets, their paths may be less predictable than scientists believed. While the term dark comet is still informal, it captures an intriguing hypothesis. These objects may be remnants of the early solar system that contain small amounts of ice and volatile compounds hidden beneath dark, rocky surfaces. Over billions of years, exposure to the sun could have baked off their outer layers, leaving them looking like asteroids. But deep inside, frozen pockets of gases may remain. Under certain conditions, perhaps when sunlight penetrates cracks or when the object rotates in a specific way, these pockets might heat up and release gas in tiny bursts unseen by telescopes. These subtle jets could nudge the object in much the same way that full-fledged comets are propelled by sublimation, but without producing any detectable tail. Understanding dark comets could have profound implications for planetary science. For decades, researchers have debated the origin of Earth's water. One leading theory suggests that comets delivered much of our planet's early water supply by crashing into the young Earth. However, measurements of the chemical signatures of many known comets do not match Earth's oceans. If dark comets represent a different class of icy objects, with different compositions or origins, they might help solve this mismatch. Perhaps they are relics of a population that once supplied water to Earth, but has largely decayed or transformed over time. Studying them up close could reveal whether their ices contain the same isotopic fingerprints found in Earth's water. Beyond their scientific importance, dark comets may also represent an overlooked hazard. Traditional asteroid tracking methods rely on predicting orbits through purely gravitational calculations. A small object that periodically accelerates in unpredictable ways is harder to track and could pose a threat if on a trajectory near Earth. If even a fraction of small near-Earth asteroids are actually dark comets undergoing subtle thrusts, then planetary defense systems may need to be updated to account for these hidden forces. Fortunately, the recent discoveries have brought new attention to this possibility, and researchers are now reconsidering how they model the movements of potentially hazardous objects. The upcoming Japanese mission may soon shed light on all these mysteries. The spacecraft, which was aimed at a near-Earth target for unrelated reasons, is now heading toward what appears to be a dark comet purely by coincidence. By the time it arrives in 2031, technological advancements may already transform how we observe and classify small bodies. But nothing compares to direct observation. The spacecraft will be able to capture high-resolution images, analyze surface materials, and detect even faint gas emissions that telescopes from Earth cannot see. It may uncover whether dark comets are icy inside, whether their surfaces are coated in carbon-rich dust that hides their activity, and whether their structure differs from both typical asteroids and traditional comets. As scientists patiently wait for the mission to reach its target, research continues on Earth. New telescopes, including next-generation survey observatories, are expected to find more objects with dark comet-like behavior. With each new discovery, astronomers refine their models, compare orbital anomalies, and try to determine how widespread these strange objects truly are. If dark comets turn out to be common, they may represent a substantial fraction of small bodies in the inner solar system. Their existence could reshape our understanding of solar system evolution and the dynamic processes that influence small objects over billions of years.